Hello, science students. Welcome to today's lesson about longitudinal waves, vibrations, and properties that all waves share. Remember from our previous lessons that there were two types of mechanical waves. The first was transverse waves that were covered in that lesson, What is a Wave? The second type of mechanical waves are called longitudinal waves. And if you think back to that lesson, transverse waves cause those particles to move perpendicular to the direction that the wave moves. In this example of a transverse wave, you can see that the wave is moving from left to right, but the individual particles are being vibrated up and down. Longitudinal waves are the opposite. Instead of causing the particles to move perpendicular to the direction the wave travels, a longitudinal wave causes them to move parallel to the direction that the wave is traveling. So in this picture, you can see that the wave is moving from left to right, as well as the particles are vibrating from left to right. Here in this animated example, you can watch some of the individual particles are highlighted there in red. You can also see the wave move from left to right. As you look a little closer, you can see that the wave moves through the particles, and the particles shift left to right in that same direction that the wave is moving. This creates areas where the particles are bunched together. These bunches are called compressions. It also leaves some areas that are a little bit more empty than normal. These less compressed places are called rarefactions. Make sure you add that definition for a longitudinal wave to your notebook. It's a disturbance that moves particles parallel to the direction of wave motion. Sometimes they're referred to as compression waves because they cause those particles to become compressed or bunched up. A compression is defined as that region in the longitudinal wave where the particles in the medium are closest together. And that rarefaction is the regions in that longitudinal wave where the particles are farthest apart. Make sure you add both of those to your definitions. And here in this example that we looked at of the longitudinal wave, you can see how those areas are bunched together in a compression and how they're more spread out in a rarefaction. Mechanical waves occur when a vibration happens. Think about a drum. You've got a drumstick that hits the drum head. As that drumstick makes contact with that drum head, it causes that drum head to begin to vibrate. That vibration creates the wave in the drum head. But as that drum head moves back and forth and vibrates, there are lots of tiny collisions that occur between that drum head and the particles in the air. Those collisions transfer energy to the particles in the air and cause them to move. Just like in the collisions lab we did last unit, where one cart ran into another one, it transferred its energy and velocity from the first cart that was moving to the one that was not. The same thing's happening many, many times on a very, very small scale. The movement that those new air particles have creates what we call a sound wave that travels through the air to your ear. The more that something vibrates, the more waves that are created. And if you think back to our rope example from last week, you can see that as well. If you moved your hand up and down only once, you got one wave that moved down the rope. When you stopped moving your hand, the waves stopped being created, but the existing waves still continued to move down the rope. And if you moved your hand up and down multiple times, you got more and more waves in the rope. But the same thing happens. When you stop moving that hand, you stop creating the vibrations in your hand, that rope stops moving, but the energy that's already in the existing waves continues to travel down the rope. Each vibration creates a wave. When the vibrations stop, no new waves are created, but the existing waves continue to travel through the medium. Let's review a little bit about some of the mechanical waves. We've learned about transverse and longitudinal waves, both of which are mechanical waves. Both transverse and longitudinal waves transfer energy, but they don't transfer matter. They both must have a medium to travel through, and they have lots of similarities that we can use to describe each wave. So we're going to use some of the same terms, whether we're talking about transverse waves or longitudinal waves. All of these waves share some of the same properties that include things like energy, amplitude, wavelength, frequency, and speed. Let's start with amplitude. All waves transfer energy from one place to another without transferring the matter. The amount of energy that the wave has depends on the amplitude of the wave. Amplitude is defined as that maximum distance that the wave travels from the rest position. Make sure to add that definition to your key vocabulary section. Let's take a look at one of the transverse waves, like the rope example. The larger the amplitude, the more energy that transfers. In the top example, the hand is moving in relatively short and small up and down motions. That creates the crests and troughs of this wave, and you can see the amplitude measured up from the rest line to the top of the crest and down from the rest line to the trough. Those are the amplitude. In this first example, that distance is smaller, and so that wave has a smaller amplitude and carries less energy. In the example below it, you can see that the hand is moving in a much larger motion. It's moving further up and down. This creates larger waves that have higher crests and deeper troughs. The amplitude from the rest line up to the top of the crest or the bottom of the trough is larger than the first wave. If you have a larger wave that's moving that rope higher up in amplitude, you've changed its position a greater deal and you have more energy. If you think back to gym class, probably in grade school, I bet almost all of you have played with a parachute before. And possibly you've put something like a beach ball on that parachute. As you shake that parachute up and down, you're creating waves in the parachute. If you're making smaller motions with your hands, smaller waves, lower amplitude, that parachute has less energy in the waves, and that beach ball would fly lower than if you had a higher amplitude wave. As you move that parachute up and down to greater extents, the ball went higher and higher and higher because the wave had more energy to transfer to the beach ball. In a longitudinal wave, higher amplitude causes greater compressions and greater rarefactions. So in the top example, you can see that the coils in the area of compression are a little bit further apart than the example in the bottom. Those coils, where they are more closely packed together, have a higher amplitude. Same type of thing. If you look at those sections of rarefaction are more closely together in lower amplitude, and the particles have moved further apart in a higher amplitude wave. Waves can also be described by their wavelength. A wavelength is measured in a distance measurement, like meters, centimeters, or quite often you might see for wavelengths that we'll be working with the measurement of a nanometer. The wavelength, though, is the distance from one spot on a wave to that exact same spot on the next wave, like the crest to crest or compression to compression in a wave. You can see we've added that definition of a wavelength to our key vocabulary section. Make sure that it gets recorded in your notebook. Let's look at the wavelength on this transverse wave. On a transverse wave, it's easiest to measure the wavelength from the crest to the crest. It could also be measured from the trough to the trough, but you want to make sure that you have the same spot to the same spot on the next wave. In this example, you can see two different transverse waves. The top one has a shorter wavelength because there's less distance between the crest of one wave to the crest of the next wave. The bottom example has a larger distance between the two crests of waves. On a longitudinal wave, we measure from the start of a compression to the start of the next compression. In this example, you can see that it's measured there at the start of a compression to the start of compression. You could also measure from rare refraction to rare refraction, just like the trough to trough in the transverse wave. In a longitudinal wave, you can measure the wavelength from one compression to the next. In this example, you can see the areas of compression in the top wavelength are closer together than the areas of compression in the second wave. The bottom wave has a larger wavelength. Waves can also be described by their frequency. The frequency of a wave is how often the wave passes. It's calculated by finding the number of wavelengths in a second. And that could be a wonderful definition for frequency, the number of wavelengths that pass in a second. Let's look at an example here, like the wave pool at Waterworld. Here you can see two people on an inner tube rising and falling with the waves as they pass. The stopwatch helps to give you the idea of the amount of time it's taking these waves to pass. On the left side, you can see that after a couple of seconds, they've gone from the top of a crest down to the bottom of the trough, and another 2 seconds, they're back up at the top of the crest. So it took 4 seconds to complete one whole wave. On the right, you can see the individual in the inner tube starting on the top of a wave. After 1 second, they're at the trough. 2 seconds, they're back up on top of a crest. 3 seconds, they're back down in a trough. And 4 seconds, they're back up at the top. They've had 2 complete waves pass in the time of that 4 seconds, as compared to the 1 complete wave that passed on the left. So the waves on the right have a higher frequency than the waves on the left. They also have a shorter wavelength than the waves on the left. Frequency is measured in a unit we call hertz. It's abbreviated with HJ. And a hertz is a measurement of how many items, how many waves pass a point in 1 second. So 2 hertz means that 2 wavelengths pass the point in 1 second. A frequency of 4 hertz would mean that 4 wavelengths pass in a second. The larger the frequency and the wavelength, the more energy a wave has. And if you think about that, the more waves that are passing through a medium in a given time, the more energy that's being transferred. One final thing to think about is the speed of the wave. Different types of waves can travel at different speeds. For instance, light is a form of a wave that we'll cover and learn about soon, but light waves travel much faster than sound waves, roughly about 1 million times faster than the sound wave, which is why you can see lightning before you hear the thunder. The medium or material that a wave is traveling through can also affect its speed. And if you think back to what we know about the particles in different mediums, like solids, liquids, and gases, they're closer together in solids and farther apart in gases. When they're closer together, That makes those collisions occur much quicker and easier and transfers the energy from one particle to the next much faster, like you can see in this example here. Thank you so much for your time. If you have any questions, please go back through and watch the video again and then send them along to your teacher.